and I work for Azure Systems. What I want to do today is to talk about, as the title suggests, high-performance microservices using Java. And what I've done is to really divide this presentation into three parts. The first part, we're going to talk about what are the sort of fundamental ideas of microservices and really why they've become so popular and such a high-profile piece of technology in the most recent times. Second part, we'll then look at how Java relates to microservices and how you can create microservices using Java. And we'll also look at some of the issues that using Java has in terms of how the JVM works in respect of containers and in respect of microservices. And then the last part, we'll look at how the Zing JVM from Azure can address those needs and give you high performance when you're developing services and applications. So as I said, let's start with the basics of microservices. Now, the first thing is that we have to understand that what we're talking about with microservices, that the principles behind them are definitely not new. This is technology that has been around for really quite a long time. And what we're actually talking about here is distributed computing. So it's the idea that we can take an application, we can break it up into a number of pieces that can operate separately, and then we can place them where we want to in terms of making most sense from the point of view of performance, from the point of view of reliability, from the point of view of load balancing, and all those types of things. And I think it's worth just spending a few moments to look at how we got to this point in terms of microservices, because it'll help us to understand why microservices as we understand them today are the way they are and why they're so important. So the first thing that we need to look at is really the beginning of distributed computing. And this kind of goes all the way back to really the 1980s when we had RPC, remote procedure calls. And the idea behind this was, as the ideas of distributed computing would suggest, separating things up so that you could call a particular procedure from a C program remotely across a network onto potentially another machine. So it could be co-located on the same machine, or it could be on a different machine. So suddenly we had this idea that an application didn't need to all be located on the same physical machine. And then obviously time went by and people came up with more requirements for distributed computing and more ideas about how to solve these types of problems, because distributed computing has a number of serious issues that you need to think about when you're developing applications. It's how do you deal with things like transactions? How do you deal with things like authentication? These types of things are very critical in terms of making sure that your application works the way that you want it to. And so CORBA, the Common Object Request Broker Architecture, was one attempt at making that work. So this was very much around the idea of objects. It was very much around the idea of C++, object-oriented programming. And so that was another approach at solving the issues of distributed computing. Moving on a little bit, then Microsoft got into the idea of distributed computing, and they created DCOM, Distributed Computing Object Model. And this was also linked into some of the ideas of what was called OLE, the Object Linking and Embedding Technology. And so that's kind of early 1990s. And that really, again, sort of led into more things, which brings us to the sort of Java side of things. And so Java has had the fundamental ideas of microservices from way back to like 1998, I think it was, when Java EE first came out. And what we have here is the idea of components. So you have enterprise Java beans, you have servlets, and these are the components which make up your application. And these run inside a container. The container is the app server, the container is the servlet engine. And then you can deploy those wherever you want to. So they don't have to be co-located in the same app server. You can put them where you want, and then through things like the JNDI, the Java Naming and Directory Interface, you can look up where those components are, and you can find them as you need them. You can also do things like load balancing, you can do things like failover, so that you can have support for making sure that if an application needs to be up a certain percentage of the time and something fails, you can fail over to a different server and use JNDI to locate that. So Java, right from sort of almost 20 years ago, has had a lot of the ideas that we use in microservices today already built into it through the ideas of Java EE, EJBs, and servlets. Then, of course, we moved on a bit, and the whole idea of web services became very big. And again, this was an idea of how to distribute the components of your application. But this time, rather than having the idea of using things like RMI, using things like DCOM to communicate, the protocol that it was built on top of was XML. XML became very popular, so along came the XML remote procedure call technology. And this sort of morphed into what then became called SOAP. This was really sort of the basis of web services. SOAP, the Simple Object Access Protocol, actually a very badly named piece of technology, but this was something which, along with things like the Web Services Definition Language, UDDI, which was used for locating services, was again a way of distributing the parts of your application in a way that you had a platform-neutral way of communicating between the components and being able to access services as you needed them. Again, that sort of changed, and we sort of dropped the P, so it became SOA. Obviously, this stands for something slightly different because this is the Service-Oriented Architecture. And this is really the forerunner to microservices as they are today. But there are some big differences between service-oriented architectures and microservices. Primarily, service-oriented architectures relies on a thing called an enterprise service bus. So that's the way that things are communicated between the different services, and you place messages onto the bus. They are directed according to where they need to go to and things like that. But microservices don't use that type of approach. So there are a lot of technologies which have come before microservices and given us a lot of the ideas about how microservices should work. Now, what has caused the rise in popularity of microservices? Why is it that now these are suddenly the thing that everybody is talking about, everybody wants to get involved in? And primarily, it's about how we develop software now. And that has changed fairly recently because we've moved away from the idea of having a very structured, very long development cycles, which are very planned and very carefully thought out, so that you have to have very long development cycles. What we now have is much more agile methodology. The idea is that our customers, our business needs to react more quickly. So we need to get changes developed more quickly and into production so that people can use them immediately rather than having to wait 6 months or 9 months or a year for those changes to make it into the applications that they're using. So we're much more seeing now the idea of an agile methodology, very quick changes are required. And that also ties in with a shift in terms of the way that software is developed into the ideas of DevOps. So now, rather than having a separate team who does the software development, they then create the code and compile it and hand it over to the operations people, who then deploy it onto the production servers, maintain that, make sure everything's running. You've now got really the merging of those two roles. So the developers now have the ability to say, right, I've created a new component, I want to push that out into production, I will run the unit tests, I will run all the tests I need to, verify that the code works, does what it needs to, and then I can push it straight into production. And that is also tied in to the ideas of continuous integration and continuous delivery and continuous deployment. So we have things like Jenkins, we have things like Puppet, we have things like Chef, which allow us to automate the process of getting the code that developers are writing, making that available more quickly, getting it into the production systems, and enabling the changes that are required by our business, by our customers, to be made available much more quickly. So this is the set of technologies which is really causing microservices to be much more popular because of the way that we need to develop software. And that also ties into the idea of how we actually architect our systems. So typically in the past, we've gone with the idea of client-server systems, we've gone with the idea of N-tier systems, where you've had a client, you've had business logic, you've had a database. But these have been very monolithic in terms of the systems. So all of the business logic is held in one particular place. All of the persistence for the data is held in one place. All of the things which drive the UI are held in one place. And microservices is about taking that and breaking it up into a number of discrete components, discrete services, which can work together to deliver the application. And those services work together through very well-defined interfaces. And the way that this is defined in microservices is through the idea of what are called promises. So promises are the interfaces between the different microservices, such that you know exactly how to access a particular service. When you want to access that service, you use the promise to understand how to send the message to that other service. You know what the format of the message that you're going to get back is. The developers who work on that particular service can then change the implementation inside the service without having to worry about affecting any other part of the system, so long as they don't change the interface that's being used from those other services. And that sort of brings us into the overall architecture of a microservice-based application. What we have on the left is our clients, our users for this particular service. And what they're going to do is they are going to want to access our service. They'll do that typically through a web browser. It'll be a web-based application. So they connect to a website, they use a URL, and that will be one of the services in our application. That service will deliver everything that the customer needs. But in terms of what happens underneath, it interacts with potentially a large number of different services within our cloud infrastructure. So it can go off to different services, it can get authentication, it can get data, it can do business logic. Whatever's required for the application can be constructed from different microservices, pulling them all together and passing messages between them. And then we've obviously got the persistence layer where we've got databases, we've got data repositories, but we can make sure that the information we need to keep is being kept in a particular way. Now, the nice thing about this architecture is that we can separate up things in terms of development. So we don't have to have one team responsible for the whole application. We can have one team that's responsible for one or maybe two or a few of the services which make up that application. People who are experts in a particular area can address the needs of those services. So if they understand how to drive the user interface, they can work on that. If they understand about security and authentication, they can work on that. If they understand about the data structures that are being used in terms of the persistence, they can work on that. Business logic, they can work on that. But they can work on the pieces which they are domain experts in. And then for other services, you can have other development teams who can use their expertise to work on different services. So it allows us to separate up who's working on which particular service and making sure that we get the best possible team for the service that we require. We pull all those pieces together and make it available as the complete application to the user. So from the user's perspective, it's no different, but internally, it's very different. And we can react much more quickly in terms of making changes. Now, the other thing that we need to look at is how microservices work in relation to virtualization. Virtualization is another thing which has become very popular in the last few years. So how does microservices sit with virtualization? Well, if we look at the most simple way of configuring a machine, what we have at the bottom is our hardware, our physical machine, physical server that we want to run our application on. On top of that, we have some operating system that abstracts away the issues of how to interact with memory, how to interact with processor, how to interact with devices, all through device drivers and so on. On top of that, we have libraries, we have runtimes such as JVM, things like that, which can be used to run applications. And then we can run a number of applications on top of that, application A, application B. That's the traditional way of doing things with a server. What we've seen more recently is a switch to using virtualization. where you have a data center where you will have a number of very large machines with many cores, many processors, lots of memory, lots of disk, you may want to divide those up so that different clients can make use of different parts of the machine. But you also want to have complete isolation between those clients so that clients can't see each other's data. That could be very bad. What we can do for that is introduce virtualization. Now, to do that, we can add an extra layer where we have a hypervisor. Now, in this case, I put it on top of the host operating system, but you can also run the hypervisor without the host operating system directly on top of the hardware if you want. The hypervisor then allows a guest operating system to run on top of it such that the guest operating system thinks that it is seeing all of the machine. Even though it's only seeing a part of that physical machine, its view is that it's seeing all of it. So it knows it has a certain number of processors, it knows it has a certain amount of memory, and it's limited to using those things. You can have multiple guest OSs, they can be different, you can configure them how you want, you can then have libraries and runtimes on top of those guest operating systems, and then run your applications on top of that. What has become more popular recently with microservices is understanding that that's a very heavyweight approach, because you have to replicate the entire operating system every time you want to put a new virtualized environment on your machine. So there's an awful lot of code that needs to be installed to make that work. What the container engine for microservices does is really about isolation rather than virtualization. In this case, we have our hardware, we have our host operating system, and then we run a container engine on top of that, which isolates all of the services above it. In that case, we can have a set of libraries and set of runtimes associated with each service. And those libraries and runtimes can be completely different. So we're not using an operating system-wide set of libraries and runtimes. What we're doing is saying, right, for each service, we will have the necessary libraries for that service, we'll have the necessary runtimes for that service. That way, if we want to have different versions of libraries, it's very easy to do that because they're completely isolated. We also isolate the data. We also isolate access to processes. We isolate access to memory and CPUs through the container engine. So this gives us a very good way of making sure that all the different services can run together on the same machine, but without bumping into each other, without being able to see things in other services that we don't want them to. Now, obviously, we can actually combine those, and we can have many layers where we can say, okay, we actually want a situation where we do want virtualization and we want isolation through a container engine as well, so that we have separate services running on top of the guest operating system. So having a container engine does not exclude the use of virtualization. Having virtualization does not exclude the use of a container engine. You can mix and match as you want to. Now, how containers work is through specific operating system support. And the container engines that we typically use today run on top of Linux, and they use two of the features which have been in Linux actually for quite a long time. Both namespaces and C groups, or control groups to give them their full name, have been around since about 2002. As I said, this is about isolation. It's about making sure that a process on the Linux box only has access to the things that we want it to have access to. In the case of namespaces, what we're doing there is we're saying that the process we have, our container, will only be able to see a certain part of the full process tree. That way we won't be able to see the processes that are associated with other services. We may not be able to see the processes which are being used for some of the low-level features, which gives us additional security. It also gives us the ability to have the same machine used for different clients, so we can't see the processes. We can do the same thing with file systems. So each service that we're implementing through a container can have access to a different mounted file system, and it won't be able to access file systems which are being accessed by other services unless we specifically grant them permission to do that. Same thing with networking. We can allocate either a physical network interface or a virtual network interface to each container, and that way we don't have to worry about using specific ports on our network interfaces because they will be separate for separate containers. Each container can listen on port 80 for HTTP requests. It can listen on port 8080, whichever port you want to use, because they're separate network interfaces. So that handles the isolation of the processes, the file systems, the networking, and so on. What C groups, control groups, allow us to do is to determine how much of the resources of the machine are allocated to each container and therefore each service. And in that sense, we can say how many CPUs, how many cores we want accessible by a particular container, and also how much of the memory. We do that so that if we have a box that has, say, 12 cores available to it, and we only want a service to have access to 4 of those, it won't suddenly start using other cores because it generates lots more threads. All of the threads that are running in that particular process, in that container, must use only the 4 cores that we have allocated to it. Similarly, we can restrict the amount of memory. So if we have a machine that has, let's say, 32 gigabytes of memory, we can restrict our container to only using 4 gigabytes of memory. That way, again, if there's some issue with the service that's running in that container and it starts trying to use more and more memory, it won't be able to go beyond the 4 gigabyte limit that we've set it, so that it won't affect other services that are running on that machine. It won't degrade the performance of those services by taking over the resources of the machine in order to do whatever it's doing. So it's very much restricted in terms of how that works. Now, that's quite important, as we'll see, in terms of the way that Java works. So let's talk about Java-based microservices. Now, as I said, in terms of Java EE, the ideas of microservices have already been around for quite a long time. We can look at EJBs, we can look at servlets, and we can say, well, those are effectively microservices. We're breaking our application up into a number of components. Those components can implement business logic, they can implement persistence, they can implement user interface parts, all separately, and we can deploy them differently. But obviously there's various things of the new microservices model that give us even more features. So let's look at how we can do that. And really, there are 3 ways that you can implement microservices using Java. Now, the first of those is what we call a containerless service. And this is really the way that we implement Java application code at the moment. So what we do is we take our service that we want to create and we compile it into a single jar. Now, I call it a fat jar, but it's not really that fat. So we create a single jar that has all of the code that we need for our service in it. It will run on a system-wide JVM that we have installed on our machine. It's going to use the system-wide libraries, system-wide frameworks that we have installed on that machine. So from a distribution point of view, it's very simple. We simply take our jar, we build it, and then we copy it onto the machine so that when we start it up, it's running whatever jar we want to run. That jar, as I said, only needs to contain the code for the service that we're building. The problem with that, drawback, is that we're using the system-wide shared libraries and frameworks. If our developers decide that they want to upgrade the service and they want to use a new version of a particular library or framework, they're then faced with the problem of how to install that on the machine. So there might be people using, say, version 4 of a particular service, a particular library, and our developers want to move to version 5. How do they install that? How do they make sure that the other services aren't affected by moving to a different version, which could potentially have incompatibilities in it and things like that? So this is not really an ideal way of doing microservices in Java. It's the simplest, but it's not the most efficient in terms of taking advantage of the real power of microservices. So the second way of doing this is to move to self-contained services. And this has become very popular through things like Spring Boot, through Drop Wizard, and through Wildfly Swarm. What we do there is, in effect, the same thing that we did before, taking all the code that we need for our particular service and putting it into a single jar. But this time, rather than relying on libraries and frameworks that are deployed onto that machine, we put everything into that jar. So all of the different components that we need, all of the frameworks, all of the libraries that we need go into that single jar. From a class path perspective, what we're now saying is that the class path does not go outside of this jar. Only where it goes outside of the jar is to take libraries from the JVM, from the standard class libraries. But anything else is contained in the jar file which we're deploying through Spring Boot, through Dropwizard. That extends right the way through to including things like a Tomcat engine, including things like a Jetty engine. Spring Boot uses Tomcat by default, Dropwizard uses Jetty. So you put all of that in there, so you've got your self-contained application. Does mean for a bit of a bigger jar, but it does eliminate the problems of compatibility issues. If you've got one particular self-contained service that wants to use version 4 of a library and one that wants to use version 5, it really doesn't matter because they're only going to use their own jar and they're going to take the library from that. As long as you include the right version in your jar, everything will work. So it's completely independent in terms of the libraries and the frameworks that it uses. What we can then do is we can extend that. So we can take our single jar, our single self-contained service, and we can then deploy that into a container. So we could do that if we wanted to have multiple JVMs running on the same machine, and we could extend the way that we deploy these things to take advantage of the way of using containers. Now, a lot of people at the moment are using Docker as a container engine, so we'll use that as our example. So what we do is we use the container, a conventional container from Docker, say, and we create our single jar. Now, we don't have to create a single jar. We could package everything into our Docker container using multiple jars. But because we've got the power of a self-contained application or service, it makes sense to use a single jar. So we typically use that. This also is nice because it gives us a consistent deployment model with non-Java services. If we're using something like Kubernetes, if we're using something like Mesos, then we can use the same way for deploying Java services as if we've got Node.js services, if we've got C++ services. It doesn't matter. It's all going through the same way of deployment. However, there are some things that you need to be aware of in terms of using Java inside of a container, because the JVM is not completely C group aware. Now, what I mean by that is that if you create a container which has your jar file configured in it and the JVM, it will run, and you can say, I only want to give 4 of the cores that I have in my machine out of 12, and I only want to give 4 gigabytes out of the 32 gigabytes I've got. The container will enforce that. The container will make sure that you can't use, the JVM can't use more than 4 cores simultaneously, and it can't use more than 4 gigabytes memory. But what's going to happen is when the JVM starts up, if you don't configure specifically or explicitly certain parameters, then the JVM will look at the system and say, how many CPUs, how many cores are available in this system? How much memory is available on this system? And despite the fact that it's running in a container, it will actually be given the results for the whole machine. So when it asks how many CPUs are available, it will get the answer 12. When it asks how much memory is available, it will get the answer 32 gigabytes. So if it uses ergonomics to determine how big the heap space should be and how many threads there should be in the common fork join pool, it's going to be a problem, because it will say, okay, you've got 32 gigabytes in there, I'm going to use a quarter of that for the heap space, I'm going to try and allocate 8 gigabytes of memory for the heap. But the container enforces the 4 gigabyte limit, and so you have the issue of not being able to allocate 8 gigabytes, and the JVM won't start up. So you need to be aware that if you're going to use a JVM inside a container, you must configure it based on the configuration of the container. So you have to explicitly say, I want the heap space to be no bigger than 4 gigabytes. I want the number of threads in the fork join pool to be no more than 4, for example. These things do need to be quite carefully looked at to make sure you don't run into problems, because otherwise your JVM won't start up. Similarly, you need to think about how much memory you allocate to your container based on what the JVM is doing. So you might think, well, okay, I want a 4 gigabyte heap space for my JVM, so I'll allocate 4 gigabytes to that container. But of course, the heap space is not the only memory that is used by the JVM. Since JVM now doesn't have a permanent generation, there are a number of objects that are used in the native memory. So there's an amount of native memory outside of the heap that is required to store things. Similarly, if you have threads, which you will have in your application, then each thread will use at least 1 megabyte of space because of the stack size. And so if you had 100 threads, for example, in your application, you're going to need at least 100 megabytes of space for the stacks for those threads. So you need to think carefully about how to size your container for the JVM that you're going to run in there. Now, JVM also has a number of challenges when it comes to dealing with microservices. First of those is, how does the JVM respond when the system is under load? What we're now doing is we're saying, let's take our monolithic application and divide it up into a number of discrete services. The service level agreement that we have with our customers who are using the entire application will determine response times, for example. So it's going to say that we need to respond within 20 milliseconds for every request that it gets for 99.99% of the time. So that's a typical sort of SLA. But the problem is that we then have SLAs internally. So we have SLAs between the different components, different services that build up our application. So we need to make sure that when we have multiple JVMs, multiple services, the system will respect the way that things are going to work. So we need any degradation in terms of, as we increase load, to be as flat as possible. What we don't want is big peaks in the graph as we start to add more load and getting a degradation in response times. This is where microservices become harder, because predicting the load between the different microservices is harder, and predicting how much you're going to respond or how much load you need to respond to becomes a lot harder. Similarly, when you're allocating resources for multiple JVMs and multiple services, that also becomes an issue, because you're going to look at each service individually and you're going to say, okay, well, here's my peak load that I need to support, and here's my nominal load. And those will normally be substantially different. If you start allocating resources such that your individual service always has enough resource to cope with the peak load, you're going to end up allocating a lot of resources which most of the time aren't going to be used. And so you're multiplying the problem, if you like, so that the sum during normal load is going to be a lot smaller. So how you allocate resources is quite a concern. And the last thing that you need to consider is how to start up services quickly and spin these services up. One of the big advantages of microservices is the ability to scale horizontally. If you've got an increase in load, what you can do is simply say, well, I'll start up more instances of this service, load balance to those different services, and then support a higher number of users of that service. So we can scale horizontally. But if we want to do that, we need to make sure that those services can start up very quickly. So let's, in the last part, look at how the Zing JVM can support the things that the JVM needs to do in the most efficient way. Now, the first thing we need to look at is how Zing JVM deals with memory management, because this is different to other commercial JVMs. What we have with Zing is we have the JVM, but we also have a kernel module which is called ZST. And that's obviously integrated with the Linux kernel such that it can reside on the host operating system. So it's not part of the container, it's in the host operating system, which means it has a view across all of the containers which are using JVMs in those containers. That's a very useful thing for us to be able to do, because by having this holistic view across all the different JVMs that are using the memory in the system, even though each container has its own maximum amount of memory, JVM's configured to use a certain amount of memory, we're actually dealing with how we allocate memory to the JVMs through this kernel module. It gives us a lot more control over how things work. What this allows us to do is to provide elastic memory, in the sense that we can adjust things to enable services to perform better, to enable services to continue to service requests, even in situations where they might not normally do so. We have a thing called contingency memory, which I'm going to talk about in a moment. And this really does lend itself to supporting multi-tenancy of JVMs on the same machine. Whether that's through containers, whether it's through virtualization, it will work in the same way. And it really does work in the way that if the number of tenants that you have, greater the number of tenants you have, it improves the efficiency of that. Talk a little bit more about contingency memory. So contingency memory is an area of memory that we basically set aside as a contingency. So that if something happens which is outside of the normal, we've got some memory set aside that we can use if we need to. And what you find is that when people determine the size of the heap that they want to use with a particular application, quite often they don't necessarily get it right first time. And they might get that wrong by making it too small. They deploy the service into production and people start using it, suddenly gets hit by a much bigger load than it's expecting. And what's going to happen is you're going to start allocating more and more memory, and suddenly you get to the point where you hit that XMX value, and it's going to generate an out-of-memory exception. Your service is going to stop abruptly, and that's really not good in a production system. What we do with contingency memory is to say, okay, we know you've got to the maximum memory that you've assigned to this, but we'll actually let you go a little bit further. So if there is contingency memory available, now, have to understand that we don't have an infinite amount of memory. So clearly, if you get all your services all trying to exceed the amount of memory that they've been allocated and we run out of contingency memory, then everything will stop. But if you've got contingency memory available, what will happen is we'll say, okay, we'll allocate a bit more memory to that JVM so that it doesn't generate an out-of-memory exception. It will go beyond XMX and it will continue to service requests. What we'll then do is we'll automatically trigger faster rates of garbage collection in that JVM, with the idea that if we start doing garbage collection more quickly, hopefully we can bring the system back into the normal bounds, bring it back below the XMX value that you've set, and have everything continue as normal. Obviously with this, you need to be monitoring your JVMs, you need to be monitoring the systems in order to determine if this is happening. Because if you see contingency memory being used a lot, then clearly you need to adjust the size of your heap to increase it, to make sure that you don't start using contingency memory, because contingency memory might not always be available. The other thing is the way that the garbage collector works. And so we use the C4 garbage collector rather than the collectors which are used in other commercial JVMs. And this is the continuous concurrent compacting collector. So it actually works at the same time as other threads. So it really does compact garbage as other threads are working. And again, this is designed very much to work in a multi-tenancy environment. The nice thing about this is that the way the memory system works is that the JVM doesn't hold on to memory. It works in conjunction with the ZST module. So it's talking directly to the kernel. So we've developed the ZST module so that it is designed to work with the memory requirements of a JVM. Rather than the memory requirements of a general purpose process, we've made it work just for the JVM. So it deals with allocation and freeing memory specifically for the JVM. This gives us a much better way of handling memory management, because we can go down into the memory management hardware and interact with that, cache lines and so on, and improve efficiency through that. So what we can do is we can say, right, because the JVM will not hold memory that it doesn't need, when it frees up memory, it gives it back to the kernel, in effect, through the ZST module. That way, when it needs more memory, and this will typically be through allocation of objects, which will happen in the young generation, and that will use what are called TLABs, the thread local allocation blocks. Now, in other commercial JVMs, what happens is that the memory that's held for the heap is contiguous. And so in order to allocate objects, you'll continue to allocate objects in the young generation until you reach the end of that, and then you'll do a minor garbage collection. Start again at the beginning and start allocating more objects. Yep, that all works fine, there's nothing wrong with that. But the problem you get is that by the time you come back to start using those blocks again, they've in effect gone cold. They've been moved out of the cache, and so you need to then bring them back into the cache. With the way that the Zing JVM works, because it interacts with the ZST module, we can actually have what are effectively hot blocks or hot areas of memory provided directly to the JVM, because when a JVM frees up a block, we've still got it in cache, we can then hand it off to another JVM to use as a thread local allocation block, so it doesn't have to be reloaded into the cache. That kind of thing can really help in terms of performance. Again, so that's kind of the key to multi-tenancy elastic memory. And what I've done here is I've actually put two graphs here to show the difference in terms of performance from a latency perspective of the platform. So we did some, or Hazelcast did some benchmarking using a 2-node system with a 1 gigabyte heap, and they compared Hotspot with Zing. So this is interesting to see, because one of the things that we see is that people often think that Zing needs a lot of memory for the heap space, but it doesn't. Just because we support up to 2 terabytes in terms of our heap space doesn't mean that you have to have a lot of memory for the heap. You can use 1 gigabyte as we see here. What's being measured here is not actually the performance of the Hazelcast. It has nothing to do with how Hazelcast is actually performing. What it's showing is when you're running Hazelcast, the latency that will be observed by the Hazelcast application caused by whatever is underneath it in terms of the platform. So that's the JVM, the operating system, and the hardware itself. So we use a thing called JHiccup to monitor what the latency that's produced by the system itself that will be visible to the application. And as you can see here, on the left-hand side, we've got the results from Hotspot. The typical latency is somewhere in the region of 25 to 40-ish milliseconds most of the time, with a couple of reasonably big heaps and one fairly big peak in the graph. And in terms of the breaking that down by percentile, as you move more and more towards the limit of the percentiles, you'll see that the latency increases. In terms of Zing, we've normalized the graph so you can't actually see a lot of detail there, but it's somewhere in the region of about 4 to 6 milliseconds is the average sort of latency caused by the platform itself. So garbage collection, operating system, whatever. The latency that's affecting the application is very, very small compared to Hotspot. And again, you can see there's no big spikes in there, which means it's got a nice flat response to it. And again, if you look at the percentile distribution, nice flat graph, which means as your microservice gets loaded, only 1 gigabyte heap, nice microservice, it's going to respond continuously in the same way. It's not going to suddenly start slowing down as you begin to put more and more load on it. Last thing I want to talk about is how we can start up services quickly. So if we look at a typical Java application or Java service, when we start up that application, the thing that we're going to be using is bytecodes. So we take the bytecodes from the class file and we have to interpret them. We have to convert them from bytecodes into native instructions. This is the whole write once, run anywhere idea. As the application starts to run, certain methods will be called multiple times because they're in a loop, they get used more frequently, and the adaptive compilation part of the JVM will monitor that and decide, oh, okay, these particular methods could be compiled, they could be inlined, they can be made more efficient. And we'll see a gradual speed up in terms of performance. There are 2 compilers in the OpenJDK JVM, there's C1 and C2, which give you different profiles in terms of rate of warm-up and overall efficiency. But the idea is that at some point, you'll be running your application for a while and you'll get to a fairly consistent level of performance based on the fact that the hotspots in your application have been compiled, and so most of the time you're actually running native code rather than interpreting bytecodes. The problem comes is when you want to start up that application again or start up another instance of that application, because you basically have to go right back to the beginning, start interpreting, go through the analysis of hotspots, and go through that warm-up period. What we really want to do is to go through the process of warming up our application, and then the next time we start it up, we want to use the information about that profile of the application and start it up from the point where we stopped it previously. Or if we want to start up other instances, we can start it up with the same ideas that we had in our initial application. So this is what we've done with Zing. We've created a thing called Ready Now. And so Ready Now will go through the warm-up process as before. So we start out interpreting, gradually analyze the hotspots, compile them until we get to a nice steady state. Then we'll record a profile of what the compiled methods are, the classes, and so on. What we don't do is take a snapshot of all of the classes and all the methods that are compiled. We can't do that because the JVM has certain rules about how it works in terms of when you start up, and it actually wouldn't be valid to do that. So we can't just take a snapshot, but we do record a profile which gives us a lot of information about what methods are compiled, what classes are loaded, and so on. That way, when we start up an application using a Ready Now profile, we don't have to start from cold. We don't quite get the initial speed that we get from the fully warmed up application, but it does allow us to start up more quickly. Use the profile, we can say, okay, let's compile these methods and get the system running more quickly. And so we get a faster warm-up profile. That way, if you want to spin up more microservices using Zing and using Ready Now, you'll get those services coming online more quickly in terms of overall performance. So just to conclude, really, microservices are very well suited to the idea of modern software development. They're focused on the idea of agile development, so we can make changes more quickly. We can use the whole idea of DevOps. We can use continuous integration, continuous deployment through the various tools that we have available, so that we can change parts of the system without affecting everything. As long as we maintain the same interfaces, then everything will work. Java microservices are a little bit different to normal applications. You need to think about the speed of startup. If you're going to scale horizontally and you want these services to spin up quickly, you also need to think carefully if you're going to run a Java microservice inside a container, because of the issues I said about configuring the CPU and the memory for the JVM so that it understands what the C group has assigned to it. You don't necessarily need a container. You can use things like Spring Boot and Drop Wizard outside of a container. There's no problem with that, so you don't have to use a container if you don't want to. Zing, as I've gone through, is very much ideal for the idea of Java microservices. The way that heap management works, the way that the garbage collector works, we scale from very small heaps all the way up to very, very big heaps, and big heaps do not take a lot of time to garbage collect. We don't have a garbage collection situation where the time that it takes is proportional to the size of the heap, unlike other commercial JVMs. Ready Now technology allows for fast startup of the services. One last thing I would say is that if you're interested in trying Zing, there is a free 21-day evaluation license available from our website. So you can go to info.azul.com, Zing trial, you can download Zing, you can install it on your system. You have a 21-day license so that you can try out your application, run your benchmarks, figure out what improvement in performance you can get from that, and decide that it makes sense to use that in production. So with that, I'm now going to switch to see whether we got some questions here. So let me have a look at the questions. Right. Right, so considering re-architecting a Java-based HP system size, what are the standards we should adopt to the process allow us to operate on a wide? Right, okay, so that's a fairly broad question. So the question is about re-architecting. Really, it's about deciding how to separate up the application into the most logical services. I think that to try and answer that question in any greater detail would actually take too long. But yeah, it's about trying to figure out how to separate up things into the most logical set of services. And there's a lot of good details about that. When running an application that utilizes thread pools that are auto-configured to use all the CPUs in a container, cause problems running bare metal containers because you don't want a container utilizing all the cores visible in the container. which is no problem. There is yes. So in terms of the number of threads that are used by the JVM, you can configure the number of threads that are used by the common fork join pool. That's one important thing. You can also configure the number of threads that are used by the garbage collector in certain situations. It's true that you can't restrict the JVM as a whole. So if you start creating more threads, that could be an issue. So yes, this is one of the things that I highlighted, is the fact that the JVM is not C group aware. That's something that Oracle need to look at in terms of using microservices to make sure it's more aware of what the system is actually doing. Can ready now profiles be used to more efficiently configure containers on the JVM to avoid resource conflicts? I don't think that's really targeted at it's not so much targeted at resource usage, although no, it's not really targeted at resource usage, because it's more about using the profile to figure out how to get the application up to its optimum level of performance more quickly. Even in a container, you wouldn't have that effect. It is really more about making sure that the application starts up more quickly rather than the number of resources it uses. What is the price of Zing? Well, that kind of depends, but we have a sort of rough price point, which is $3,000 per server. And we actually don't count cores and CPUs, but we're very flexible in terms of how you actually want to do that. So the best thing is to talk to one of our salespeople about that, so that you can discuss your requirements and what type of servers you're using, how many cores and things like that. So we are very flexible about how we price these things. And with that, I think that's all the questions that I see at the moment. And since we're about 5 to the hour, I think I will actually end the webcast there. So thank you very much, everybody, for taking part and listening. I hope it's been useful. Thank you.